Hello and welcome to my presentation, The History of Math, Part 2. Ancient China, similar to other cultures, unified and needed civil servants to accommodate the giant empire. But these civil servants uniquely had to take an exam to prove their scholarship. This promoted the creation of textbooks with examples and methods to provide the scholar with the ability to determine a category of a particular problem and solve it. Some famous examples are the Book of Numbers and Computations, the one seen on the left. Their number system was basically the modern structure for our base 10 number system. They had similar knowledge to other cultures, such as finding the square roots or the Pythagorean theorem, but they had interesting uses of geometry, such as using two poles and proportional triangles to find an area of a city block, or being able to solve a system of both linear and higher order equations with a form of Gaussian elimination and synthetic division. The standout scholar of the era was Qin Xiaoshao, who first published the general method for solving systems of linear congruences in his mathematical treatise in 9 sections. This is the famous Chinese remainder theorem, which used a more advanced version of Euclid's algorithm. The Chinese remainder theorem was first seen by Sun Zi in the 3rd century. India has a long history of math, perhaps going back millions of years, and throughout various invasions and new kingdoms they formed one cultural unity. It appears that the study of astronomy was the main driving force behind their study of mathematics, usually to study calendrical or questions or give astrological advice. Their number system seemed to be learned from the Chinese, but they improved upon it by adding the zero. Brahmagupta was the greatest mathematician of this era, and he wrote on many algebraic concepts, such as solving remainder equations with their own version of the Chinese remainder theorem, deriving a solution to the Pell equation long before he was ever born or his culture, and he even managed to accurately approximate sine with an interpolation scheme. Additionally, they had a solid understanding of geometry, such as being able to square the circle or having an inaccurate but very precise value for pi. The late Indian period saw many innovations and developments, such as their creation of combinatorics. One example of this use was to find out how many different combinations of a perfume they could make from a number of ingredients. They were motivated to innovate trigonometry for the sake of sailors who needed to more accurately navigate the Indian Sea, using more accurate values of longitude and latitude. The Indians primarily used half chords over Ptolemy's whole chord, and the more modern term for half chord is sine. They filled out extensive tables using various methods of approximation, such as the half angle formula. The most accurate value for approximation was the power series that was developed by the mathematical school of Madhava. They had made multiple power series to approximate sine, cosine, and arctangent. And these power series could become more accurate using a pull yourself up by your own bootstraps approach. By adding more terms, they could improve the approximation step by step. On the left is an example of a graph they used to derive the power series. The Muslim empire was wide-reaching, and they had the belief that studying math and science beyond practical needs could lead to religious enlightenment. It was this belief that propelled them to be the epicenter of math and science in the medieval age. They adopted many mathematical practices from many different cultures they interacted with. For instance, they adopted the Indian number system and finalized it into the modern version, including the modern numerals we use and decimal fractions. They also adopted the Greek style of geometric proofs, as seen in Euclid's work, The Elements. The greatest mathematician of this age was Al-Khwarizmi, who is the literal origin of the terms algebra and algorithm. He defined them in his book, which was a manual for solving linear and quadratic equations using specific systemic algorithms for subtraction, addition, finding a square root, but it was the specific step-by-step nature that made him famous. Al-Khariji did much work in algebra, specifically in intermediate equations, and used Greek methods of Diophantus, but his greatest contribution was the creation of inductive proofs. In the late Islamic period, Al-Samuel made significant advances in polynomials, such as coming up with negative coefficients and exponents and finding out how to multiply, divide, add, and subtract them. In addition, he related algebra to arithmetic and showed the Arabics move away from the Greeks' approach to using geometry for algebra. Al-Banna reworked the Indian combinatoric system into an abstract version and derived the modern combinations formula. The Muslims were very interested in trig, specifically spherical trig, for its ability to find the location of Mecca relative to themselves. One chart of this could be seen on the left, and finding what time of day it is so they could pray at the proper time. They took Ptolemy's and India's trigonometry and vastly improved upon it by defining all trig functions, finding the spherical law of sines, and producing the rule of four quantities. However, it was the religious focus that became their undoing, as the intolerance of so-called foreign sciences caused a decline in mathematics until the mantle of mathematics was eventually passed to the West. After the fall of Rome, Greek entered a dark age, and mathematics entered the hands of the Christian Church. There was not much innovation because they were focused on preserving what they thought of the classics of astronomy, music, arithmetic, and geometry. Their most use for math was to create an accurate calendar. Interestingly, the Pope Sylvester II introduced the Islamic number system, but without the zero during this time period. Western mathematics finally took off when a group of Jews in the Spanish city of Toledo translated the great works of Greek and Muslim mathematics. One of these Jews was Abraham Bar Haya, who took after the traditions of Euclid in his contributions to geometry. Ingeniously, he found the area of a circle using the visual proof seen on the right. Imagine an infinitesimal amount of threads that form a circle. If you unwind them and stack them, they form a triangle, whose height is the radius and whose circumference is the base length. You can use the triangle angle theorem to find the area of a circle. In addition, he constructed the first Western chord chart. However, it is different from the original Greek's one because he found arcs for given chords instead of for angles. The last Jew that I want to talk about is the one that shares my name, Levi Ben-Gerzon. He gave proofs for combinational formulas that combined the mathematical rigor of Greeks, but also the induction type of proofs of Islam's. Fibonacci is the most influential mathematician of his period because he introduced his sequence, which led to many advances in monochrome fields, such as architecture. He, most importantly, summarized Islamic advances and introduced them to Europe. This led to the widespread use of such things as the Arabic number system. His successor, Jordanus de Muir, his work represents the structure of Western mathematics, a combination of methods used before but with our own advances. For example, he used a combination of Islamic algebra problems but Euclidean rigor and formality. and he made his own contribution with using letters as symbols for mathematical problems. However, this all came to an end near the end of the 13th century due to many sources such as the Black Death or the 100 Years' War. But luckily, it will soon get a revival, a renaissance.